Okay, so welcome everyone to the lecture number 9. Lecture number 9, where we wish to continue with our discussion on modes of convergence. So last week, I guess to sum it up, okay, so we talked about convergence of because our evolution operator is defined by a series, operator value series, right? So we try to narrow down what it means for this kind of series to converge, and we basically came up with the idea that a convergence of this series, of operator value series, is basically determined by the convergence of a positive value number value series, the series of norms of this of our operator value series, which actually coincides with the mode of convergence that we call the absolute convergence, which is good kind of convergence. And we came up with a couple of criteria, tests for convergence, a ratio test, D'Alembert's ratio test, and a comparison test, which was like a basic tools. And what else? Oh, and one more thing to note, probably, is like when you have a series that's absolutely convergent, that is, its convergence is controlled by by the good behavior of its series of its norms, then you can think of it as like the value of this series is determined by if you set some accuracy threshold, you can reach you can get the value of the series up to this accuracy, but by there's a finite number of terms you have to sum up to get to this accuracy. And this absolute convergence tells you that the accumulation of any excess terms can be simply disregarded because it will sum up to something that's smaller than your accuracy goal. So it's so you can imagine that if you want to determine more precisely the value of your series, you just add more terms to the score, right? If n values, n terms gives you, let's say, 10% accuracy, then you basically know that if you add 5 more terms or something, you will get a little bit better accuracy. Okay, so it's not like, you are summing up, and at some point in the series, there is a term that's 3 billion times bigger than everything else. It's not like that, okay? Absolute convergence, which we are interested in, is gives you this nice picture, what controls the outcome, the value of what we are doing. And that's why the absolute convergence is so useful, because it's allows you to prove many properties so that your series can actually be looked at and treated manipulated as if it was actually a sum of some number of terms, not this abstract limit, which is a procedure in the end, right? But yeah, so I think that's the summary. So now we move on, because okay, let's move to the next section, 2.2. I entitle it Radius of Convergence. Radius of convergence. Convergence. Only difficult words to spell. So the thing is that, okay, so we are interested in, ultimately, our interest lie in the evolution operator, which is not simply a series of some given terms. Those terms actually depend parametrically on the argument, on time, right? For example, of our evolution operator. Our evolution operator is a function in the end, right? And so the terms of its series are also functions. So this brings like another layer of complications to our story of series and their convergence. Because now, you know, there are some additional questions that come up now. For example, is it like for every value, for every possible time, does it still converge? Whether this rate of convergence depends on the value of the parameter of time, if it's a function, you know, how do you differentiate it? How do you integrate it? All this stuff, right? So this is another layer of complication which we should try to unravel a little bit and explain what's going on here. So to answer this kind of questions, let us consider a sequence of functions. Okay. So sequence of functions. So we will have t. Let's imagine that this is a function in time, and we will have t maps to capital U1 t, which is actually equal to the first term of our time-dependent series. Okay, next term in the sequence will be U2 t, which would be U1 plus U2. Okay, so I'm creating, because we are talking about series, which is a sum of terms, and we take a limit of increase the number of terms in the sum. But this can be, of course, equally well viewed as a sequence of terms where each term is like a partial sum. So this is like a universal language we'll use here, and we can like continue, right? Free term. Okay, so we know where this goes, right? The infinite term is where you sum everything, right? But the main point that we want to isolate the issue that this is a sequence of functions, right? And now, okay, so now to talk about convergence of this sequence, I guess the most straightforward way to deal with this, because this is a new object. Terms of our sequence are not things with a specified value, right? They are functions. So how to deal with that? Well, the easiest, most straightforward way would be to just take it and convert it into a sequence of valued terms. With functions is quite, the easiest way you can do is simply evaluate your function for some given argument, right? So we can simplify this problem by converting it into a valued sequence. Convert it into valued sequence. I don't know if this is a proper wording. Function sequence, valued sequence. What do you know what I mean, right?
Function valued, number valued. Yes.
Well, it's operators, for example. So
Okay, so operators.
there is some value assigned to it. Because function doesn't have values, right? And we can do it by, let's say, so U01, UT02, U3, T0, and so on, right? We just pick some T0 in some domain and just evaluate values. And now we have just a sequence of valued stuff, and we know how to deal with convergence here. We have our definitions of convergence.
This is still a set of operators, right?
Yeah, it could be operators. I'm using hats here because our goal is operator value, but if you have number valued, function with values in some numbers,
Basically, you have, in the first one, you had operators for each time, right? Because it's, sorry, each term is a function of time.
Yeah.
And in the second one, you just fix one time for all arguments. Okay.
Yeah, exactly.
These operators were functions of time. These operators are just operators.
Are values.
Yeah,
Exactly. But now we are dealing with something that has a value.
Yeah.
Right? We can work with that more easily. So this leads, if you do this kind of conversion, this simplification, this basically leads to something that's called pointwise convergence. Okay, the concept of pointwise I think I'm dyslexic.
Yes.
You just now realize that?
Yes.
I always thought that maybe I'm a little bit stupid, but
No. You are 100%.
Really?
100% sure as a person with diagnosed dyslexia, you are very dyslexic, or rather, you are rather autistic, and in autism you have also the kind of slide that tells you that
kind of tracks,
language is hard. So, it's like, I've been diagnosed with autism 2.5 years ago, and if I remember the questions were asked, you will find it.
Whom among us is not autistic to some degree?
In
every
now it is less autistic.
Slightly.
Look, in every person there are two wolves. One is autistic, the other one is ADHD. Yes. And they are fighting for dominance.
Only for you, me, Hubert. The rest of society don't have those wolves.
I don't know.
We have our society here, okay?
There's
Yes, this is the safe group. This is the safe space.
Okay, pointwise convergence. So let me word it down. So first the words, then the formal epsilons and quantifiers. So I will torture myself by writing it down. So for each t belonging to some domain D, right? Maybe some interval, maybe infinite interval, there is some domain, and an arbitrary chosen error, and an arbitrarily chosen error, which is of course epsilon. This is our accuracy goal. There exists a value u infinity, so the same kind of convention of notation we used on previous lecture, and a threshold. Threshold is a difficult word. See, because this H is like double duty. Fresh and hold. It's like this. N epsilon and T. Such that all elements of the value sequence the one we had above, so U1, U2, past, and epsilon T differ differ from ut by less than epsilon. So this is, if you want to use words, you would say this. This is convergent. So for each t, so we pick t and an arbitrary accuracy goal, epsilon, there exists a value, this is the limit indexed by t, and the threshold n, which will depend on epsilon and t in general, such that all the elements of this our sequence past this threshold index, they differ from the limit, the goal, by less than our accuracy goal. This means that this is a convergence, definition of pointwise convergence. And now in more elegant, formal way, we would say then, for all t belonging to domain, there exists the value, the limit, right? The order is important, such that for all epsilons, there exists n, the threshold, t epsilon, such that for all k greater than n t epsilon. Isn't this a beauty? It's like
those fancy settings.
Right. All these were translated into mathematical symbols.
yeah, it's less than epsilon. Isn't this a beauty? There's so much content, right, in one line. Basically, what I wrote here, it's like, perfect.
So here, when you say for each t, so and lower you wrote for all t. So
Yeah.
is it for a given t, or we have to do it for each point in the domain? You have to show that it converges. What's the logic? Because both are different, right?
You see, for each t belonging to a domain, it's a point-wise convergence in this domain,
Yeah.
right? So there is a domain.
Yeah.
So maybe we should, we could add here another couple of quantifiers. There exists a domain,
Yeah.
if you wish, but this is just.
Now, my doubt is, so let's say our domain is from 0 to 1, including, for the same. And my doubt is, should you show for each point in this domain, this converges, or it is sufficient that at least one or two is converging? So what's that?
Convergence in domain,
Yeah.
point-wise convergence, it has to be in some domain. You say, okay, so this is the domain where it converges, okay? This is like a definition of convergence, okay? We are not checking in what is for what values it diverges. We are saying what it means to converge. So we have this domain, a converge in the domain. If you want to converge in the domain, pointwise convergence, that would mean that for all values of the argument in this domain, you have to converge.
Yeah, so all the points should be considered.
Yes. Otherwise, if
Okay.
one of those points is you're not converging, then it should be in the domain of convergence, right? It's like because this is a definition of convergence, right? We are not testing yet. You can imagine if we were just given some series and we're trying to narrow down what is the domain where it converges, right? You would have to investigate this. But here we just say what it means, convergence. And of course, the order here is important, right? Because we say first we pick a value, the argument. Then there is where the convergence, the limit value, which is dependent on t. And then for every accuracy goal, there is a threshold that also should depend most likely on the choice of accuracy and the argument, such that past the error is smaller than, and so on and so forth. The standard This is like standard stuff, right? For convergence. The innovations are here. And then, okay, so if we have convergence in this mode, then we could define a function, because we are starting with a sequence of functions. So it would be nice to, maybe speak of a limit in terms of function as well. But with this simple construction, pointwise convergence, all we can do is basically define the function define a function in the following way. So we would have, let me scroll down, some function ut such that it takes arguments from the domain D, and then it assigns to each argument the limit of this pointwise convergent sequence U, T, K, which we denoted by this formula. So this is a new function that, as to each argument, it assigns the limit of a value sequence. Okay. So this is what is happening here. So that would be like the straightforward way, the most simple way to deal with our initial problem of sequence of functions, right? And because it is so straightforward, it's pointwise convergence, it's also limited in certain ways. I mean, it's simple, so it's not too powerful, okay? Meaning that not when you go, because you want to have powerful ways to converge, because you want to be allowed to do a lot of manipulations on your sequence or on your series, right? The more fragile the convergence, the more conditional it is, the less you can do before everything breaks, right? And this mode of convergence is not powerful in the sense that it doesn't guarantee a lot of resilience to manipulations, okay? Because it's not really sequence of functions converging into a function. That's not what's going on here, right? We have constructed like artificially a function that assigns limits of those valued, those simplified sequences. Okay, it's not like a clean. It's not something that we would be proud to say that we have like lim k goes to infinity t u t k, limit of this equals something like this. Okay, this is not what's going on here. This would be ideal. This is what we are looking for. We have a sequence of functions, and it converges into a function itself, not some cobbled together on spit and string, some kind of construction that's probably very fragile, right? We want this. This is what we want. This is what we got. This is not enough. We are not happy about this. So how to achieve this dream? And it turns out it's kind of simple, actually. But to like realize what is the thing we have to do, let us re-examine this pointwise convergence first. So the idea is like we pick a value t, right? And then pick the value t, we pick the accuracy goal, and then we are looking for this threshold value, right? Beyond which the difference between the limit and and the terms will be smaller than the accuracy goal. And naturally, the threshold value must depend for sure on the accuracy goal, right? Because we tighten our accuracy, that means we have to dig deeper into a sequence to actually get closer to our limit, right? So it's natural. We always wrote it that this n depends on epsilon, but also it's already written here explicitly because we are looking at, we are taking our sequence of functions and we convert them into a sequence of valued sequences, right? Which are more or less independent of each other, right? So for every t, we are creating a new problem, new convergence problem with some valued sequence, right? So even if we pick the same accuracy goal for all those independent problems, there is no logical reason to expect that this threshold value will also be the same for all those guys. It most likely will depend also on the time, t, which is how we create our individual problems. And this dependence of the threshold on t is what really makes it into separate problems into this rather than this. This is the issue, right? Without some extra constraint, we will never get here because of this dependence on t. So what is the solution? Well, simplicity itself. Let's just demand that threshold does not depend on t. Okay? Which leads us...
Isn't it narrowing the problem?
It is. It is, I mean, it's narrowing, but also...
It's worth it.
Yes, exactly.
The maximization of the
Well, we just redefine another mode of convergence. We defined another mode of convergence. So now we are in the realm of definitions, right? Then, when we have definitions, we can do theorems and see what are the relations. And the tests and criteria and blah, 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 and so So we have so we are led then to another mode, so-called uniform convergence. Uniform convergence. So I have here some words, fortunately not many of them. The value sequence. The value sequence. Let's write it here. Converges uniformly for t in the domain or on the domain, in the domain. I'm not sure what is the standard wording for that. When, and let's just stick to our nice quantifiers. For all epsilons, so for any accuracy goal, there exists threshold such that for all t in the domain and all k greater than threshold, the error is bounded. T infinity. Okay, so we switched places of our quantifiers, right? Now it's t is behind the threshold because we demand for n to be independent of t.
And why this is called uniform?
Uniform because for all t.
So why can't we just say that we just pick the maximum of all the possible n of epsilon? That should be
now you are thinking about what comes next.
Probably the Hamiltonian.
You're,
like that should solve this problem, right?
well,
Because you already assume that
spoilers.
Spoilers. You're thinking right. Wait for it.
You're on the.
so you already assume that each t converges. So that means there exists n of epsilon for each t. So that means you should be able to, n of epsilon is always a number, so you'll get a bunch of numbers from which you will be able to find a maximum. So
You are thinking like Weierstrass, basically, okay? Which will
Weierstrass, okay.
They will be Weierstrass uniform convergence criteria.
It was a compliment or not?
Yeah. I mean, he already went one step quite,
Weierstrass
for you obvious step, but very, very good, very good. While we at it, this is like the definition, but this is the definition that we don't like because it's unconstructive, right? And of course, you have a uniform version of Cauchy criteria also, right? If you have, doesn't matter that we shuffled some quantifiers here. It's still still have Cauchy stuff. So equivalently, so we continue. Equivalently, we have a Cauchy całuchy uniform.
Przesuwam całuchy. Wszystkie maile do Ciebie by tak zakończyć. Całuchy.
Convergence criteria. Which is, as all Cauchy criteria would be for all epsilon, there exists thresholds only on epsilon dependent such that for all t in our domain and all n greater or equal m greater than threshold, the sequences are getting closer. They're being squeezed. Okay, so that's a Cauchy version. But still, so you could also have a Cauchy criterion for pointwise convergence, right? We just have to, exchange the quantifiers and make threshold depend on t again. Obviously, right? And so this is like this is what we'll be using. This guy is like just a basis, a fundament and foundation. Sorry, definition that's foundational. So in this case, when we have this uniform convergence, so now you ask why uniform. Are you satisfied with the answer that it's uniform because it's all the whole domain is the same rate of convergence? Because why I'm saying rate because this threshold, right? If the threshold is let's say small, I would say that you are very converging very fast because you don't need to go very deep. If threshold is big, you are converging slowly because you have to dig deeper. So now, because n, the threshold is independent of t, for all t is the same, is good. That means that the rate of convergence is uniform across your domain. That's why uniform convergence. Okay, fine? And that's the name convention. So now, in this case of uniform convergence, we are no longer held back by this yuckiness, and we can actually say that our function sequence converges into this limit sequence. Okay, which is nice.
Isn't there a summation with the Cauchy convergence criteria?
Sure. So if we are explicit with our symbols, and because you are partial sums, basically, right? So we can, if I expose everything, this will convert into.
So basically, the upper index is standing for the sum up to that term.
Yes, partial sum. You know,
It's not the nth term; it's nth term of the partial sum.
Yes. That's why this notation is so cool, because it's like partial sum to infinity. Yeah? Clever, huh? And u k t smaller than epsilon. If we unravel it. But I decided that it will be less confusing if we focus on sequences for a second. Okay, and now the practical way to distinguish uniform convergence from merely pointwise convergence is something to side grade to our toolbox, or upgrade is something that Sarat already invented. It's Weierstrass. In reality, it's Weierstrass. Sorry, he was earlier.
Yes. Lost a chance to publish a maths paper.
Oh my God, Weyer.
But Weierstrass isn't he German? I thought
Austrian, German.
Should be
Yeah,
some kind of Germanic person. But
there's also the other guy, right? Bolzano. I don't know. Bolzano Weierstrass theorem. I don't know which one is that.
Test. It's probably one of Weierstrasses, because it's usually whole clans of.
Yeah.
I don't know which one it is. I don't know which year it is, which century. But I think I managed to pinpoint that there is a name attached to this. When this is let's just write it down and go over the very short proof to explain what's happening, and basically to show that your intuition was 100% correct. If we are looking some tests, convergence tests, criteria, side grades, you can almost always be sure that there will be some, you bound something with something else and something more simple. This is of course the same game is played here. So where do I have it? Let W, it's W because Weierstrass.
Yes.
Well, double S is not there.
Yeah, we don't want to go there.
Even more German, so
Oh, no.
My problem whenever I work with the sulfide bond. They are two sulfurs, so SS.
Sequence.
Okay, other way to write it down.
Sequence. Oh my God, I butchered this sequence. I hope it's sequence.
it's okay.
Of non-negative terms such that the norm UTK is less equal to W. So we have a domination for all, but the twist is for all T in the domain, because this dominating sequence is just numbers, value sequence with fixed number independent of T. There's one guy that dominates all on the whole domain. Okay.
German.
So we have a domination, and then if W, if this guy converges. Oh my God, no. Converges, then the tested sequence also converges. Then K1 UKT converges, but uniformly. For T in the domain. Okay, so this is the statement. So if you find a guy that dominates and it converges, then the dominated stuff also converges, but uniformly, so more powerfully. And the proof, it's of course, sometimes it's very instructive to look at the proof, and this one is very simple. So proof, and it explains maybe a little bit what's going on. So the proof is like when this guy, the dominator, that's cool, converges. So it means that then this means that for any epsilon, for any accuracy threshold, and large enough n, m, and then m, so indices. So if it converges, this means that there is a threshold, and beyond that threshold, you take two guys, and you have the following estimation. So epsilon will be greater than the so basically Cauchy criteria, m plus 1 n wk, right? This is what convergence means. That we have all those indices that we can find. But this guy is greater than the sum of our tested series by the domination, and this by triangle inequality is greater than. So this is basically we are recreating the same argument as we used for a comparison test previously. However, we have here additional things we can get, because so we have a convergence of W. So we pick epsilon, we get a threshold for W, right? And we find that for this threshold, this threshold, one threshold value, we have this Cauchy criteria satisfied for our function sequence. Okay, for our function sequence, which means that we found n, the threshold, that is independent of t, right? So in other words, instead of like checking if looking for this threshold that is good for every t, we can like identify this threshold immediately with the threshold of the dominating non-function sequence, right? So this is what Sarat said basically, right? Okay, if you are looking for a threshold that's good for every value of t, so find the biggest one, and then it will be good for everything else. So this is basically this kind of reasoning.
And is that last inequality interesting, because it looks like it also tells you something about the remainder. The norm of the remainder will be always less than the individual norms added up, right?
Yeah, I mean, this is so we have this is Cauchy criteria. We are showing that if this converges, this satisfied Cauchy criteria. So we can say it converges uniformly. Okay, so that's why I did it.
No, like
So the contents is the same as a Cauchy criterion. So it says what Cauchy criterion
yeah,
says.
because like in my head I think of it like when you're trying to bring the norm inside the sum, you'll end up with an inequality. So that's what I was aiming for. That
Yeah, I mean this is triangle inequality, but in reverse.
yeah, okay, that's why. Okay.
Because I thought it would be fun if I start from epsilon, right? I just psych. I'm playing with your perceptions. Just if you mirror it, it will be normal. Yeah, so that's uniform convergence for you. That's a Weierstrass uniform convergence test, the best test. Basically, you don't need anything more. And now, so I was advocating for uniform convergence because it's. I said it allows us to say that we have this, so the function sequence of function converges into function, but it also that would be just talk, But actually, it turns out that now you start investigating stuff. This uniform convergence is like a basically necessary ingredient for all the stuff that you would like your limit function to have, right? And I have a list of things that I want to give to you here without proof, because because too much work would be to. Although I looked, I made an effort to understand the proofs, to realize what they mean, what they are, so that I could decide you don't need to see them. I spent a lot of sweat, blood, and tears to actually compile it. So we have a couple of things. So where things where uniform convergence is important. It's important. So one, continuity. Right, we have a functions, so like the most basic thing about functions is to check if they are continuous. So we have our sequence, series of functions, of terms that are functions. If I go to the limit, can I preserve continuity, for example? Or will it break? And as it turns out, I have good news for everyone here. When the terms of a function series U K T are continuous. So we start from we are summing continuous functions. That's good. We have to have some basis, and the series of those terms from 1 to infinity converges uniformly. Formally, its limit is continuous. Is continuous. So uniform convergence gives us guarantees that the whole sum will be continuous as well. We won't lose continuity. If it wasn't, it was just pointwise convergence, you can come up with examples where this breaks. So if you want to be sure that nothing wrong is going on, you have to take care of uniform convergence. And the inscription, the equation that like illustrates this quite nicely is this. So I take limit t going to t0. So this is what continuity, we're testing continuity of limit n goes to infinity of a partial sum ukt. So this would be in our series, the limit, and we are looking for continuity. And this equals to limit n goes to infinity k1n limit t 0 u k t. Okay? We switched the order of limits. Okay, so this is a nice way of thinking about this. Uniform convergence allows us to switch order of limits. Okay, this is like a slogan, a bumper sticker.
But it will be every limit, or just this specific limit?
I mean, continue. Right now, I mean, what are other limits?
No, you can always have some parameter that you want to compare. Yeah.
Well, then you would have to show that it's uniform in this other parameter as well. Okay, this guarantees you. Okay, that this will happen. You can exchange so this is a bumper sticker.
Then you also have now for every parameter you will have a whole range of t, and each t will also give you a sequence. So it's like a tree of.
And one more thing about this is like because of this equation, we can actually. So we want to like if you want to calculate this limit t goes to t0. It basically like defines you what you have to do, because this thing is like a nebulous. It's a procedure, right? It's not like concrete value you can work on, but it tells you uniform convergence allows you to. Okay, so just go to the limit first on the terms which you have written down, the formulas, and then you can just sum them up and get your result, and it will be the same as if you first summed and then went to limit. So this is like a constructive thing. It tells you how to actually execute this continuity kind of thing. Without this, you are just toast. I mean, it's difficult to work. It's even difficult to define what this would mean actually. But it's possible to define, but it's complicated. So that's one. So I just list those guys and we go to break. Second thing, integration. Integration. So maybe I will just say it without writing. So when your function series terms are integrable, so you have to start from, your terms are something. Integration makes sense for the terms themselves before you sum them up, and your series converges uniformly. Okay, so terms have to be integrable and a uniform convergence. Then okay, so imagine that uniform convergence. I wrote here uniform convergence. Then you have another exchange of limits kind of formula. Integral limit n to infinity k1 to n u k t dt. So that's something we would be interested in. So integral of our evolution operator, for example, but we don't know how do I integrate and take limit at the same time? Difficult. But uniform convergence tells that, oh, you know, this is the same as first integrating term by term and then going to the limit. Okay? Which is another constructive thing. We know how to do it term by term, and then just go to the limit. And the uniform convergence guarantees that it will be the same. Okay? Again, exchange of the derivative. Derivative. So this one is a little bit more tricky. Because you need a couple of things here. When the function series k1 to infinity, that's my place, utk converges. Wait, I lost my place. Okay, when this series and the series of term by term derivatives so k1 to infinity derivative converge uniformly, then we have another constructive thing. Then we have derivative of the limit kt equals limit of derivatives. So again, if you, this we know how to do, this would be tricky, right? And we actually did this in like one of the first lectures, and I was trying to show that this x of Hamiltonian, the evolution operator, satisfies Schrödinger equation. I did this. I did the derivative term by term and said, oh, it's fine. And as you can see, for it to be fine, the evolution operator would have to be uniformly convergent, which it is. We'll show it soon enough, but this is the ingredient, right? And the extra conditions here is like, okay, the series itself have to converge, but also this series has to make sense, right? That's why you have to have like, right? It has to, I mean, it's kind of natural, right? If this was some crazy exploding to infinity, nothing would make sense, right? So it has to be well behaved so that you can execute the derivative. And yeah, okay, the product, we talked about product previously, so no reason to go for more. So yeah, let's take a 5-minute break, okay? Okay, so let's continue. Yeah, it's all nice and good. So we have our uniform continuity. Yeah, now this gonna come in. Yeah, okay, very good. So now the next thing on the docket is a thing where all this that like focuses all those things about modes of convergence. Like there is one kind of series that like collects. It's like the one series, you know, in the like the one ring, you know, in the darkness bind them and so on and so forth. It's like the kind of series that collects all the modes of convergence into one place, and it's very useful for that reason. And I'm talking here about power series. Okay, so special, yes, a very powerful series, special kind of series.
Very serious kind of series.
Yeah, very serious kind of series, exactly. Exactly. And this is a power series. Power series. Power series is basically something, let's say power series on complex numbers. So it will be a function of, let's say, complex numbers in general. And it is so there are some coefficients, and the dependence is like this. Okay? That's why power series, because terms are powers of your argument. So if you take this kind of power series, for example, Taylor series is a kind of power series, right? So it's commonly seen everywhere. We all seen them and love them. And now the thing, so if you take a power series like this and perform a ratio test on it, okay, one of the tests for convergence, for absolute convergence for that matter, let's perform the ratio test on this bad boy. Okay. So ratio test will tell us, okay, so we have this ratio R. It will depend on Z, okay, because Z. And they say, so go to the limit k to infinity of the u k plus 1 Z norm to u z k. Right? You take next guy and the previous guy and the guy and the next guy, and you look at the ratio, go to the limit. And depending what this value is, you have convergence, divergence, or you don't know. And for power series, this is actually very simple. K plus infinity, because it reduces to just, so we have C k plus 1, the coefficient, this coefficient, which is some complex number. And we have I lost my cursor, absolute value of Z to power k plus 1, very easy, Ck, Zk. So this simplifies. So we have Z and the limit of the coefficients. Okay, which is also the same as saying that this is Z over a limit k to infinity Ck plus 1. That's just a thing I want to do here. I just move it into a denominator. Nothing fancy happened. So this thing. So for this series, this power series to converge, this ratio must be less than 1, right? Which depends on Z. This will put some constraint on what Z's are allowed before everything breaks, right? And this Z, it's not constrained on z itself, but on the modulus, absolute value of z. So it like defines a radius, right? So-called radius of convergence. The concept of radius of convergence for this series, which is basically if we want this series to converge, so this to be less than 1, this is the same as saying that the z, the absolute value of z, must be less than this thing in the denominator, which is some positive number. Finite might be infinite, k plus 1. And we will dub it R, capital R. And this guy, this positive number R, defines a radius of a disk. Right? So we will have a disk centered at 0 of radius of R, okay? Which would be defined as a set of all complex numbers Z, such that the absolute value of Z is less equal to R. And
That's equal to.
Come again?
So it's equal to, it's included.
So disk, I think it's with a boundary.
Okay.
Right? Disk is.
A ring will be at R, and
but
what will be less than R?
But the convergence.
Yeah.
So this our power series, it converges inside the disk. Okay, because it has to be on the boundaries.
Test is inconclusive.
Are complicated. What happens on boundaries? That would the boundaries would correspond to a ratio equal 1, which is inconclusive. Which means that there is something happens. Yeah. Usually, it's because there is a pole somewhere, okay, or some branch cut or something. I mean, it's not bad. You can usually like go around the pole, but then things stop being unique, and you have start to depend on process and stuff like that. This is like inside this disk, everything is absolute convergence. Okay. So we know that inside this disk, the power series is absolutely convergent, so it's very nice. We don't know what happens on the boundary, and beyond it diverges, right? But there is more we can say. Although we don't know what's happening on boundaries, we know that the series is also uniformly convergent inside its domain, inside this radius of convergence. Why? Well, you can do the formal proof, but basically, I mean, we already figured this out. I mean, you have a power series, so you can bound it. You can easily bound it with just set for Z value just before the boundary of your disk, right? So if you said Z smaller than R minus some epsilon, arbitrarily small epsilon, right? I mean, for Z smaller than okay, sorry. If you set Z equal this, right? Then your series ck Z, this guy, I mean, even its terms, ck, for each ckz smaller than this value, this is of course less than ck r minus epsilon, right? This is obvious. I mean, c. Okay. So right? So we know what is the bound. Immediately, easy to figure out what is the bound. A very nice bound, and we know that this series will converge because it's inside the disk. So Weierstrass theorem tells us that, okay, so it converges absolutely and uniformly. So power series are very nice because they, bring everything. They are the best kind of series when you are working inside the radius of convergence. Okay. They are the nicest thing you can have. And having said that, we can move on. We can move on to the next point. Finally, after all this hard work, we can talk about convergence of evolution operator.
Like a power series.
Sorry?
You can write it like a power series. I mean, it's a power series.
So yeah, let us summarize. So we have our series defining evolution operator, right? What is the procedure to check that it converges and how it converges? Absolutely uniformly. We of course love to uniform convergence. Absolute uniform convergence because we want to be able to say that it satisfies Schrödinger equation. We want to justify our previous claims, right? So it would be good to know. So what is the procedure? So again, we start with some operator value series, which is complicated, difficult. So the first step is to bound it with something, right? So that we have to worry about the convergence of this bounding number value series. And we are dealing here with a functions, operator value function series. So we want to have a bound that's good for all domain, right, also. So we have one number series that bounds our function for all the arguments we are interested in. And the bonus points if this bounding series is some kind of power series, right? So then we investigate convergence of this bound. If we find that it converges, then through Weierstrass theorem, we know that our evolution operator will converge uniformly and absolutely, which is very good. So the trick is to find the good bound, and the best scenario would be if there will be some kind of power series. Because it might happen that our bound might converge, but in the radius of convergence is maybe not trivial. So basically the bounding series, the ratio test is not r equals 0, which would mean that, because if our r would be 0, it would mean that the radius is infinite, right? Because this is, right? If r, small r, ratio is 0, right, this means that the radius is infinite. This is radius of convergence, which means that our disk is whole space, which means then we will have converge absolutely uniformly everywhere. The best kind of thing. There's no constraints at all. So, but we have our evolution operator. We find bound. Maybe this bounding series converges, but the r is not 0, maybe something. So that would introduce some kind of constraints, probably on the domain of our operator then. So it's like important stuff. That's why this concept of radius of convergence. So it's a nice shorthand for saying that we are converging, but there are some constraints. Although we are converging very nicely, uniformly and absolutely, which is the best thing. So once we find our radius of convergence, then we know that we have we can derivative, we can execute it by doing a derivative term by term, and it's fine, everything converges still. We can integrate if we want to, we can multiply to evolution operators, and we know that everything will converge because absolute converges and stuff like that. So it's like, this is the procedure. have our guy bounded somehow with number series that's good for the whole domain, bonus points if it's power series, figure out the radius of convergence, and voila. The radius will be inherited by our series. And this is the procedure. So to actually execute this, so the easiest way, we already investigated this, like for free, if you have your operator values series, for free you get a bounding series made out of norms, right? This is like for free. It might not, I mean, we might not be sure if it converges, for example. Maybe we have to bound that guy with another guy or something like that, but this is a good starting point. So finally, we have to decide what are norms for operators. Right? Because so far we just use norms. It's fine. But now we have to calculate something for our concrete operators. And now it's time to make a decision. So we will talk, first thing to break down is an operator norm. Operator norm. So there is this, because you have operators, naturally those operators act on some vector space, right? So you have you have our Hilbert spaces and stuff like that. So we already start with your norm for vectors, right? So it's like the standard procedure is to basically inherit this norm, construct the norm for operators with using the norm of your vector space. This is like a standard. You don't always have to do it, but it's like a standard thing. And the way usually people construct it is like the norm. How big is your operator is how much it's like stretches vectors it acts on. This is like the idea. My operator is big when it makes vectors big. It's small when it makes vectors small, right? So if it shrinks vectors, you would say that my operator is small. If it makes them big, it's big. Which leads to let's say not canonical, but like a standard definition of operator norm, which in our case, like I said, will be induced by bracket, right? Because we have a norm for vectors, our Hilbert space, so we will recycle it. And the norm for this like standard norm, let's say, is defined the following way. Norm of the operator is max over cats living in our Hilbert space. So it already has some optimization inside. And you take a norm of a vector produced by the action of our operator and normalize by the norm of the vector we are acting on. So the idea is to isolate this stretching, how much it stretches. Okay?
You should avoid the zero vector, right? The definition. The zero vector has zero norm, so we'll run into trouble. Psi should not be the zero vector.
It is 0 over 0. So.
Yeah,
I think that's also in the definition.
Okay. If zero vector wouldn't be good because zero vector has zero norm.
Yeah, so that.
So max, not zero. Okay, if you want. The maximization is. Sometimes people say max over norm 1 vectors, normalized vectors already.
So size or eigenstates of these operators?
Not really.
There will be connection. We will talk about it in a second. Because it's like, what if I pick, are eigenvalues somehow related to this norm? So to make it, we can make it explicit with brackets, which is also probably good to see. Because the norm, we know our norms is in a bracket notation, we know what it is. So I will acquiesce to your demands.
Yeah, judge.
So just to realize what this means, what you would have to calculate. So this would be a norm of this guy, right?
Mm-hmm.
And this would be a norm of the denominator. Square roots are because norm has square roots, right? Square root of the square of the.
Just to clarify, so you need the existence of adjoint for this.
Hilbert
Yes,
space,
yes.
yeah.
So all operators will have, and second, all operators will have norm by this definition, because then now you have bounded and unbounded, right? So it's this is already defining norm for everything.
Yeah.
Why
This is a good definition.
Okay.
This is a good definition. I won't be proving that it is a good definition.
So the maximum will always exist. That's the question. Or is it like
yes,
if it exists, that will be the...
It might be infinity, for example.
Okay.
Then it's unbounded. I mean, if you are worried about existence, you can replace max with supremum, which is actually probably what I should do. But we are finite dimensional
because
Hilbert
like, in my
spaces.
head, I don't see how this will help you to distinguish bounded and unbounded. That was my... Because it seems to say that every operator will have a norm, which means you don't need unbounded. So that was my doubt. So something here, maybe I'm missing...
Unbounded means that the norm is infinite.
Yeah, we restrict ourselves to, like, there is a max value or max.
But we are dealing with, implicitly we are always talking about finite dimensional, right?
Yeah,
then it's everything is bounded.
Fine. Forget my question.
Yeah, but to be super precise, you would use supremum here instead of max. The difference, for those who not in the know, the difference between max and supremum is like supremum might not be reachable, right? But it's like, what if we could? Then it's like, so if you don't have, if you want to be safer, you're worried about existence, you put supremum basically. Okay. Stretches are set this, and so this is one definition that we can pick, but of course not the only thing that we can do. I mean, already you might be miffed a little bit that it's using optimization, max. It's like it's not really practical, right? It's like we have to search whole Hilbert space.
Moreover, it just gives you the information about the maximal value. So if it stretches uniformly, all operators, it has the same norm like the operator.
That's a very pinpoint.
Just a one line, and the other can shrink it, and the other it could be a projector.
Yes. But still, it is very nice. It is like a good basis. But to show that it's not the only way to use norms. The simplest example I can come up with is like these operators form vector space actually. Okay, and you can add to this vector space inner product. You can make it a Hilbert space. That's fine. So if you come up with a inner product for your operators, you can have a norm induced by this canonical norm, right? So an example of this is a Frobenius norm, actually. So one of the ways to make a very nicely behaved inner product for operators is the Frobenius inner product, which Frobenius There is R here actually. Frobenius. I didn't notice that before, and it was like I don't remember how I was calling it, but it wasn't the right thing. Frobenius inner product. And it is defined. It is a very nice guy to work with, actually, and it's a trace A dagger B. Okay, so this is very nice inner product to work with.
The Hilbert-Schmidt
Yeah.
was a norm.
This is not
I think it's Hilbert-Schmidt.
maybe. I'm not sure. I know it as a Frobenius, but maybe it's a maybe it is. I'm not sure. But this is a very nice. This is very nice in a product, and the norm it could induce. So Frobenius norm would be just trace A dagger A. And just to make a point, what is trace? If you pick a basis, you calculate trace by taking a sum, let's say, of psi in some basis, psi A, dagger A, psi, square root. No, square root is over everything. Square root here, square root, okay. No, wait, no, good. Square root over everything. Yeah, this is fine. So I want this form. It's nice because it like shows the difference. So this one is looking for a maximal stretching. This one is like an average stretching. So this is what you said, right? It will make a difference between a operator that like uniformly stretch everything a little bit, and the one that's like very focused on something. This will be the one that's focused. According to this norm, would be very big, but according to this norm, will be small, right? So it's like a different kind of beast.
Now an actual question would be like, because now all your radius of convergence will all depend on the norm that you're choosing. So, but physically you cannot have physics depend on the mathematics. So, what is the equivalence between the two?
It can depend. The convergence in norm can be. You might sometimes be forced to specify which norm.
Yeah, so there should be some equivalence between.
However, fortunately, in the context that we are interested in, so finite dimensional vector spaces, be it operator space, it's a finite dimensional vector space, be our original Hilbert space, whatever, there is a theorem that's called norm equivalence. Okay? So it turns out that from the point of view of convergence, it doesn't matter which norm you use in finite dimensional vector spaces. If you have convergence in one norm, it also converges in every other norm. Because all norms in finite dimensional vector spaces are equivalent. Equivalence means norm equivalence, norm. So for any two norms, so let's call one norm A and the other one norm B. So this is you put argument here. There exists alpha and beta greater than 0, so constants, two constants. So this is the definition of equivalence, okay? Such that when I multiply alpha A, I will get something that's no less than B, and the other way around, beta. And I wrote it like that because this is like a uniform constant. For all vectors, for all things we are measuring, it works. So I take my operator A, I measure it with norm A, measure it norm B, then I get two different numbers. But there is this constant alpha, okay, that when I multiply my A norm, I will get something that's bigger than B norm. And also vice versa for beta. So this is a norm equivalence. Two norms are equivalent when those constants exist. And they are uniform so it's not like dependent on what you are measuring. Okay? And the theorem is that for finite dimensional vector spaces, so this includes operator space or Hilbert space of Katz, all norms are equivalent.
So now, yeah, just because from this, I think it would follow that now you can have equivalence classes of norms.
Yes.
Right?
Yes,
and
exactly.
then that means you can represent. You will be able to find unique elements from unique norm from each class. So for a finite dimension, I could guess how many n classes are there?
I don't know, man. That's too difficult question.
Yeah, but the other two norms, the Frobenius and the other one, are they in the same class or different classes?
Yeah, this is equivalence in the sense of equivalence classes. The norms are, in finite dimensional vector spaces, all norms sit in one equivalence class.
Okay. So there's yeah.
Right.
Yeah. So it's yeah.
I believe this is what it means, right? Yeah. So and you can see, because you can always adjust which one is bigger with those constants. So if you have because to get convergence, you have to have norm must be less than some epsilon or something. So let's say you find that you have something smaller than epsilon in one norm, and then okay, so I pick my beta constant or whatever, and I also show that if I measure it with the other norm, it also will be smaller than epsilon. So you are safe with convergence. You can always rescale such that nothing misses you.
So will they agree on the radius of convergence? I think they need not.
Radius of convergence. Radius of convergence is something that attached to the dominating series, power series. Okay.
Because because I didn't quite catch how, if you have two norms, at what aspect is this helping to make them equivalent?
Because you are looking for, let's say you find that you want to bound your series, your operator value series, right? Yeah.
When you're finished.
Okay. You bind it with some norm, right? So it immediately, because of equivalence, it also bounds with any other norm, right? Radius of convergence is associated with a radius of convergence of this dominator.
That you can choose such that both of them are.
Yes. So if you have radius of convergence, it is for the bounding guy, and this bounding guy will bound everything.
Everything in the same class.
In all norms. Yes.
Yeah. Okay.
Yeah. Okay. So it's it's because we are bound. The separate question is maybe what is a minimal bound, right? Because that would be the tightest radius of convergence. But we are not talking about this here. This is actual real question, because you might have too tight bound, for example. Maybe you can. You might underestimate. Underestimate the radius. You might with some bounding, you can find out that my radius is not very big, but it's actually could be made bigger because my bound is not very good. I just was sloppy. But this is problem for other things. Yeah, question.
Is this norm equivalent for norms, for different norms, or a given vector space, a given Hilbert space, or what? Because, for example, in the previous two norms, the Hilbert space on the Frobenius was of operators, and the other one.
This is.
Well, the inner product on the on the top is defined by the hyperspace of the states, and in the bottom the inner space is defined by the hyperspace.
This norm is norm for operators, operator space. It uses vector space as a part of its definition, but is a norm for operators. So the vector space we are measuring those two norms is a vector space of operators. Okay, and then finite dimension means that I should be able to find alpha and beta such that I can, Frobenius can be, and it's I think you can calculate it. There's a way to figure this out. This constant, and this is the definition of equivalence. And the question is which norms are equivalent. And the theorem says that in finite dimensional vector spaces, so for example, vector space of operators here, all norms are equivalent, which is the powerful thing to say and to know, because we don't have to worry now.
Yeah, and because this, you see, even though it says equivalence, like you can think of a scenario where you end up calculating some parameters for the experiment which might depend on the norm that you're using. So how will you take care of that scenario? Because it should not depend on the norm.
You just have to be cognizant of it.
Sorry?
You have to just remember that this is the case. I mean, you're doing some, the results you get, estimations you get, they do depend on norms. Obviously, they have to depend on. But as it turns out, the convergence is independent of norms. But the values you calculate, this will depend on norms, and it's a different norm will give you different numbers, and you have to tell when you are doing comparisons with other people calculations, you have to be specific. How do you get your estimation?
It feels a bit awkward because let's say you're talking about some rate, a decay rate of your density matrix or something, if it depends on the norm that you're telling, the decay rate should be physical. It should not depend on.
It's like units. You are just selecting units.
Okay.
Right. If you're sloppy with units, don't tell anyone what you are using, what units you're using. You can get difference of 2 pi, for example, because your frequency is, you measure it you actually measure 2 pi time frequency or something. It's units. It's basically units. So this tells us that you can rescale your units, which is good. I mean, it makes sense. But if dimension is infinite, there are, weird. It's probably related to unboundedness, basically.
So these alphas and betas, for every norm A and B, they are unique. They can be picked to be unique. Yes, so that it works for any vector that or operator in this case.
I don't believe it's unique. Probably you could 2 times alpha would be. Also
okay. I just meant that there is a choice of alpha and beta that is good for anything that we put into these norms.
Yes, exactly.
It's not so that I have to
it's like uniform.
Make it for every case.
Yeah, because if you said equivalence is when for every thing you are measuring, for every vector, for every operator you're measuring, you can find a number. This will be always true.
Yeah.
This is stronger.
Unless something is infinite, but it's also the other.
Yeah, but this is stronger, right? This is one fit all. Okay, otherwise it wouldn't make sense. Okay. So will we converge our? You know what? Let me write down the. Let me write down the properties of norm, and then I will blue ball you, and we will show convergence of next week. Well, this is my life. Too bad. Okay, so properties of norms, which we'll be using extensively, because as you can see, probably calculating this guy, because we will be by default we'll be using this norm, standard norm, okay? And because of this optimization built in, it's like not a thing you calculate often, but it's useful to like estimate stuff, to do bounds. We are interested in bounds, so it's actually very good for bounding stuff. Okay, you don't actually optimize, but because it says optimize, you can also, this is no less than something. It's properties. Some properties. Some properties of op norms. Of norm or norms. Some are unique for this standard norm, some are universal. So norm 1, 0, property 0 means that norm is 0 if and only if we are dealing with 0 operator. This is required by any norm. This has to be true for any norm. Okay? 0 operator means that operator that when acts on something zeros it. So this is like a property that has to be there. Next is scalar scaling. Scalar scaling. This one is also universal for operator norms, I believe. So you have some scalar alpha times A. This will be equal to absolute value of the scalar times norm. So scalars are not important for any complex alpha. Okay, so you can just pull them out or pull them back, depending what you want to do. Triangle inequality, triangle inequality. This must be true for all norms, for standard and Frobenius in particular. So triangle inequality is like a bread and butter of almost everything we do here. We already use triangle inequality extensively, of course, but just to point it out. For operator outputs, maybe output scaling. Output scaling. This one is unique for the standard norm. Actually, Frobenius doesn't have this in this particular way. It's like when you look at the norm of a vector, an output of action of A, this can be bounded by the norm of A times the norm of the vector.
It's Cauchy short, right?
No, for Frobenius that would be. It's not Cauchy-Schwarz. This is. I mean, you can imagine this. We could probably figure out how this. If you imagine that divided by, I mean, if you take this divided by the normal vector and then maximize it, you will get this. And because you are maximizing, it must be no less than this. That's why you get it. But it is useful, right? So if you are, for some reason, have to estimate vector rather than operator itself, you can like simplify it immediately.
This is the maximum eigenvalue.
The next, give me two more properties and we get there. Because it's just asking for, what about eigenvectors? It's just asking for it, and it's very much. Next, this is very important. Submultiplicity. No, submultiplicativity. Submultiplicativity. This is true for the standard norm specifically, and this is perhaps the most important. This is the reason why we use it. Submultiplicativity means that if you have a norm of product, AB, standard stuff, right? This can be bounded by norm of A times norm of B. So it's multiplicativity, but because it's bound, so that's why it's sub. Okay, sub multiplicativity. And this one is right. This is why we need standard norm basically. And 6, this is spectral radius. Spectral radius. So as it turns out, there is a connection between spectrum of operator, that is eigenvalues, and the norm of operator. And I don't remember. This is for standard norm for sure. Let's say this is for standard norm to be safe. I don't know for Frobenius. So if you put in the norm of any Hermitian operator, so this is Hermitian, it actually turns out to be equal to max over the spectrum of this operator okay, so we say the norm equals the absolute value of the largest absolute value of eigenvalues. So the largest eigenvalue is norm. Well, because it might be positive number, you have to consider the absolute values, which I will just I will come up with this kind of notation for it.
For Venus, if we're tracing, we're tracing h squared, then we are summing. It's the one norm of the eigenvalues. One norm.
Yeah, that would make sense. So this is max because this would correspond to like taking a supremum norm, sorry, instead of one norm. Yeah. So this is true. This is true for the standard norm. Okay. For Frobenius, it would be, like you said, probably a one norm of the whole spectrum. And this is for Hermitian operators. For non-Hermitian operators, so for any standard A, not necessarily Hermitian, we only get like this. It's still connected, but it's from below.
Mm.
Okay, but we will not be dealing with non-Hermitian operators, basically.
Spectrum A.
A. Yeah, exactly. Exactly. Yeah. So let's finish this. So from here, basically, if you have this and you have this, bounding the evolution operator is trivial. Okay, but let's leave it for later. Okay, so that's it for this week.